So the theory of chemical kinetics, of course, is very old and is really the foundation of chemistry and chemical engineering. There are a wide variety of models for specific chemical reactions that have been developed. Also, in the area of electrochemistry, there's a further complexity, which is that there's a charge transfer that goes on when a chemical reaction occurs. And again, there is a long history of theories. In the case of electrochemical reactions, which I'd like to focus on, the classical model for describing the kinetics, or the reaction rate, is the Butler-Volmer equation, which is about 100 years old now, and is widely used and fits a variety of experimental data. And the Butler-Volmer equation was originally just essentially an empirical expression that fit experimental data. And then starting in the 1950s, a microscopic theory of charge transfer developed, initiated by Marcus, who then later won the Nobel Prize in chemistry for that work. And it was also advanced by many scientists, even in Russia, for example, Levitch and Dogodnadze and Kuznetsov, since it was very strong actually in that field. On the other hand, I would say that in spite of all that knowledge of electrochemical kinetics, a gap in the modeling and also its application to various important systems such as batteries or electrodeposition is in coupling the understanding of what happens at the molecular level, sort of a single charge transfer event, a single chemical reaction, with collective behavior of many molecules at a larger scale, at the mesoscopic scale. An example of such a phenomenon, which I believe is important, is the coupling of chemical kinetics and also electrochemical kinetics with charge transfer to phase transformations. So there are important problems today, including some that I'm working on, which motivated me to get into this area, where the chemical reaction is coupled to some species of chemicals that are interacting very strongly with each other and undergoing phase transformations. So that is sort of the extreme limit of non-ideal thermodynamic behavior. So the classical theory of chemical kinetics essentially says that the reaction rate in, let's say, the forward direction is proportional to the concentrations of the reactants. Okay, that's the simplest assumption. And from a physics point of view, I would characterize that as a mean field approximation. We know how many molecules there are. The rate should be proportional to that number of molecules. But more generally, we have to go beyond that and start thinking in terms of activities and thermodynamic corrections. And that sort of approach has been developed in chemistry, but more can be added, and that's something I've been trying to do. So, as an example, imagine we have a reaction that's involving insertion of a molecule into a solid. So there's only a certain number of available sites. So the forward reaction cannot be only proportional to the concentration of, let's say, the molecules that are in the surrounding medium, but it somehow has to be related to the number of vacancies which are available in the solid. So the way chemists normally get around that, they view the vacancy as a chemical object. So it's a chemical species. And they say, well, the reaction is still proportional to concentrations. It's just the concentration of the particle times the concentration of the vacancy. So you just need to, it's still sort of standard chemical kinetics. But then what do you do if you're inserting into a solid and now it's actually disordered? So we're not exactly sure what's a vacancy and what's a particle, because it's not simply on a crystal where you have a clear reference. And what if we have very strong elastic interactions? So for example, when we insert the particle, it creates a huge strain and expands the solid in one region. And that expansion then affects neighboring regions and hence affects their reaction rate. And so you start to get to very coupled systems where the reaction kinetics has to be sensitive to the thermodynamic state of the material. So how much entropy does it have? How many empty spaces are there in the system? So that's configurational entropy is obviously important. Elastic stresses can be important, I mentioned. Also enthalpy, which has to do with the interaction between particles. So when a particle wants to insert itself, is it attracted to other particles or repelled from them? So that also needs to be taken into account consistently in the reaction rate. The extreme case of that is that of a material which undergoes phase separation upon insertion. So imagine I take a molecule, when I insert it into a solid, it is very strongly attracted to other molecules of the same type that are already in the solid. Such a system may have two or more stable states. For example, it might have a full state at high density of the inserted particle, and it might have another thermodynamic equilibrium state at low density. So if the material has phase separated into high and low density phases, and now I have a new molecule that is trying to decide should I insert myself or not, then that reaction rate, sort of the decision of that molecule, is not just a function of concentration, it must be a function of thermodynamic state, because the high and low density phases are already stable. So in fact, what can happen, and is something that I've predicted through my work, is that the molecule would insert itself at the phase boundary. So in other words, the reaction rate has to be sensitive not only to concentrations, but to concentration gradients, because the part of the system which is the most thermodynamically unhappy is actually the phase boundary. So if a new molecule is going to come in, it doesn't want to disturb either of the stable phases, the high and low density. It wants to insert itself right at the phase boundary. And when it does that, it propagates the phase boundary. So an example of that, kind of a theory, what it can predict and something that I've worked on, is that in an intercalation or insertion process like that, if you're inserting into a particle or through a surface that has two or more stable states, then you can get a propagation of what I call an intercalation wave. It's basically that the insertion happens always at the phase boundary, that propagates the phase boundary, and so it's kind of like a bunch of dominoes that start to fall down one by one. You fill sort of layer by layer, and you have a wave sweeping across the surface. That's very different from the typical predictions of chemical kinetics, which would tell you that the reaction starts at the surface, inserts material uniformly, and then it kind of diffuses in. So in the case of a particle, people talk of a shrinking core behavior, where you have kind of particles inserting at the outside of the particle and coming in, versus this intercalation wave, where you have sort of an ignition of a new phase somewhere by a nucleation event, for example, or a spinodal decomposition process, and then that phase transformation sweeps across the particle fed by the reaction. So I've developed such a theory motivated specifically by lithium-ion batteries. So there is actually many important materials for lithium-ion batteries that have this property that when lithium is inserted into the host solid material for storage, that it undergoes a strong tendency to phase separate or undergo other kinds of phase transformations. So the not classical, but the most well-studied example of that I've worked on is lithium iron phosphate, which is now a widely used cathode material for high-rate lithium-ion batteries. And so to really understand the behavior of that material, especially in nanoparticle form where the surfaces become more important and reaction kinetics has to be sort of handled more accurately, it becomes very important to understand this coupling of reaction kinetics with phase transformations. And in the course of that work, I also stumbled upon what I would say is a new physical phenomenon. So I just described to you that if you have a phase-separating system, then under some certain conditions, you can get, when a reaction occurs to insert a new material, rather than sort of proceeding from the surface inward, it can actually proceed along the surface as a reaction wave, basically, where you sort of have a reacted region, unreacted region, and it propagates because the initial and final states are thermodynamically stable phases. However, that behavior only happens at sufficiently low driving force. So what was a surprising discovery to me a couple years ago from my group was that, and this was predicted by our new mathematical models, is that if you demand a higher current, for example, it's a battery, and in a battery we can control the discharging rate. So we might be going at a much higher current than sort of the propagation of this boundary would allow. Or, for example, we may take a particle which it's not electrochemical, but it's just a chemical reaction. Let's say it's a bimetallic particle. It's an alloy of two different metals, for example, copper and gold, or platinum. And I stick that particle suddenly into a new solution, so it's exposed to a completely different chemical environment, which may trigger a very harsh reaction with a huge driving force. That's another example where you have a chemical reaction coupled to phase separation or phase transformation, but with a very large driving force. A general prediction that we made, and that came out of theories that I developed, is that at sufficiently high rate, you will suppress phase transformation dynamically. So you can have a system where if you turn off the current, it will phase separate or phase transform into two or more stable states. It will decompose. But if you are holding if you're driving the system with a large flux, then the energy gain from phase separating is overcome by the energy cost of driving a current through a small region. Because as I just explained, we have two stable state phases with a boundary between them. And when that boundary propagates, the active area is a little strip of phase boundary between those phases. And so that's fine if you have a low current, then a small number of molecules can go into that boundary and move it. But if you demand a higher current, you have a larger driving force, then you need essentially a huge overpotential or a huge resistance to drive the current through a small area. And so even though the system would prefer to phase separate, it then spreads the reaction homogeneously in order to allow more particles to arrive. And so you can have phenomena such as, like let's say lithium-ion battery, you halfway fill the particle at a high rate, it stays homogeneous because it's being driven so hard, and then you turn off the current and boom, it phase separates into the two stable states. And then you turn the current back on again and you lose the phase separation. And so you have this dynamical process of suppression of phase transformation. I think that's the most interesting prediction so far that's come out of this new theory that marries chemical kinetics with non-equilibrium thermodynamics. And in fact, it leads to some interesting, you could say, new states of matter. Because when we're at near equilibrium, we understand that there are different thermodynamically stable states of a system, for example, a high and low density phase. And I've also described that when we're at very high current, then the molecules are just sort of rushing in and diffusing around, and that's in a solid, you might call that a solid solution behavior. So in between, we have what we call a quasi-solid solution. What that is a system which is trying to phase separate. It's trying to undergo phase separation, but it has just enough forcing that it never quite can succeed. So it appears to be sort of frozen in a solid solution-like behavior, but it's actually out of equilibrium and trying to phase separate. So we call that a quasi-solid solution. And I think that concept is very general. And in fact, I'd just like to close by saying that this theory has many possible applications, some of which I happen to be exploring, other than just lithium-ion batteries, which is in fact where it came from over the period of the last 10 years or so. So for example, in ballistic impacts, you could have, for example, a projectile which hits a material very hard. It's well known that you can have different shock waves that are emitted, where one can be a pressure shock, where you sort of compress the material, but somewhere behind it is another shock wave that is interpreted as a phase transformation. For example, a crystal can go from crystal into amorphous, so a change in structure. But they lag behind each other. And so the question is, in that brief moment between those two shocks, what's going on? We have a system which is somehow out of equilibrium and it wants to phase transform into amorphous, but it needs a certain time to do that, and there's a certain energy driving force required, so it's delayed. And so that's another example of a sort of quasi-equilibrium state of matter, which is sort of held out of equilibrium by the large driving force. And there are a number of other applications of that I'm currently exploring, and I think this is looking forward to the future. I see that this is really a new area of research. If, for example, you're absorbing a gas into a porous material, there's the phenomenon of capillary condensation, which is that in a small pore, you first coat the walls with adsorbed molecules, and then suddenly you can fill the channel with liquid. So you have a transformation from sort of gas to liquid. But that depends on the pore size. And as you're diffusing into a porous material, you have these sort of sudden phase transformation events. And again, if you're doing it at high rate, you can sort of interfere with those phase transformation processes and have them be out of equilibrium in a way that is similar to the batteries. And so I think just generally looking forward, the coupling of chemical kinetics of adsorption and reactions, especially in porous media, at high rates in systems that undergo phase transformations is an exciting area for research in which I expect a lot of advances in the coming years.